Good morning. Today I am going to take R's complement and R minus 1's complement in digital logic design. Till now, we have seen number system and conversion of one number system to another number system. What are the number systems we have discussed? We have discussed decimal, binary, hexadecimal, and octal number system. And we have seen conversions from one of the number system, any one number system, namely either from decimal to binary, octal, or hexadecimal, or binary to the other three conversions, and vice versa. So now coming to the complement, we have two types of complements, namely R minus 1's complement and R's complement. Okay, so in the 2's complement, why we need this R's complement and R minus 1's complement? So for processing data in machines, machine language is nothing but the combinations of zeros and ones. Machine will process all the data in terms of zeros and ones, that is binary. So the machine language is 0 and 1, whereas human being can easily understand only the decimal number. So the R's complement and the R minus 1's complement is done with decimal and binary. Okay, so for example, we know that decimal number is base or radix is 10. So if for tens R's complement, it will be tens complement, and R minus 1's complement will be 9's complement for decimal. Whereas for binary, R's complement is 2's complement and R minus 1's complement is 1's complement for binary. I hope you understand. And so first thing we will see about R's complement. Okay, first thing we will see about R's complement. R's complement, the first number is nothing but 32626. Let us take it for example. So R's complement, let us deal with the first the decimal number. So the decimal number, how many digits we have in this decimal number to the base 10? 32626. It is to the base 10. It is nothing but how many digits we have? 1, 2, 3, 4, 5. So total number of digits is 5. So for taking R's complement, okay, for taking R's complement or tens complement for the number, okay, for the number 32626, what I will be doing is 10 power 5 minus, I will subtract this number. Okay, so the result is nothing but 67374. This is nothing but the tens complement of the digit 32626, where you will be using this R's complement and R minus 1's complement in dollars while processing data in the computers. Okay, so next thing is we'll take an example with the decimal number 35.62. Okay, 35.62 is very simple, pretty simple. So 10 power 2 minus 35.62 will be having the 65.38 will be the answer. And the next one is 2's complement of 11001. Now we are going to see the 2's complement of the binary number. 2's complement of binary number. We know this is the binary number. The binary number base or radix is 2, and again how many digits we have here? 1, 2, 3, 4, 5. So 2 power 5 is to the base 10, whose equivalent is 32 in decimal, and 32's equivalent binary number is 100000, that is 2. Okay, that is to the base 2. So let me subtract 30, and for example, if I need to take a 2's complement of the given number 11001, what I need to do is I'll subtract this 2 power 5 minus, okay, this is equivalent to 2 power 5, okay, decimal minus the given number, okay, the given number in binary. Again, meaning this 2 power 5 decimal has to be converted into its equivalent binary, and then only you need to subtract the given number. So after that, I'm ending up with 00111 to the base 2. And if it's a fraction or the decimal number, so 1 minus 0.0010. So how I'll be doing this is, we know this is a whole number. How many digits totally we have in the subtrahend? 1, 2, 3, 4, 5. So I'll be taking 1, 2, 3, 4, 5. Then I'll subtract 0 1 0 1 0. If like that I'm doing, I'll be ending up with 0 1 1 0 as a result. Okay, 0 1 1 0 as a result. You can check it. Okay, you can check it. Is it clear? So the decimal point, I can insert this decimal point, which is nothing but 0.110. Okay, later I can insert it. Later I can insert it as 0.110. Subtract it and check. Okay, subtract it and check. The next thing I'm going to discuss is about the r minus 1's complement, which is nothing but the 9's complement and the 1's complement. 9's complement for the decimal number and 1's complement for the binary number. Okay, 1's complement for the binary number. So 3 2 6, I'm taking the same number only. 3 2 6 6 2 6 I'm taking. So how many digits I'm having? Total number of digits is 5. If I need to take 9's complement, it is 10 power 5. Okay, 10 power 5 minus 1, since it's 9's complement, so minus 1 minus the given number. So this is the answer. Okay, and for a decimal number, we know that this is 10 power minus 1, this is 10 power minus 2. What I will be doing is 1 minus, okay, for the decimal number, 1 minus 10 power minus 2, the given digit is 10 power minus 2, minus 0.62, this is 0.37. For a decimal number. Of a fraction, I will be taking 9's complement like this. Okay, and the third sum is, let me take 35.62 as a whole number. Okay, as a whole number, meaning involving the decimal point also. So what I'll be doing is, how many number of digits I'll be having before the decimal point? 2 digits I'm having, so 10 power 2. Okay, how many digits I'm having after the decimal point? Again 2, so 10 power minus 2. Okay, 10 power minus 2. I need to say why we are taking this as 1, because this is 0. 10 power 0 is unit place is 0. 10 power 0 is 1, so I'm taking 1. 1 minus 10 power minus 2 minus the given number. Whereas here I'm having 2 digits. This is 10 power 2. This is 10 power 2. You're getting me? Yeah. Yes, 10 power 2, and then this will be 10 power 2 minus 10 power minus 2 minus 35.62. Okay, 35.62. Okay, so 10 power 2 minus 10 power minus 2. Okay, and then minus 35.62. On the other way around, I can even take, instead of 10 power 0, I can even take, since there is no digits involved, I can instead of 10 power n, this is nothing but 10 power 0, which is equal to 1. So that one only I am carrying it here. Okay, that one only I am carrying it here. But here we are having 2 digits here. So this is 10 power n is nothing but 10 power 2. That is what we are carrying it here. So 10 power 2 minus 10 power minus 2 minus 35.62, which is nothing but 64.37. And the next one is 1's complement of a binary number. Again, how will you take the 1's complement of binary number? This is nothing but 1 2 3 4 5, 2 power 5 minus 1. Since it's 1's complement, this is decimal number. The resultant you take convert the resultant into binary and then subtract. See, this is 2 power 5 is 32. 32 minus 1 is 31. 31's equivalent is 5 ones. So 1, 2, 3, 4, 5 minus 1, 0, 1, 1, 0, which is nothing but 0, 1, 0, 0, 1. Okay, 0, 1, 0, 0, 1. This is your ones complement of 1, 0, 1, 1, 0. Let me take then a decimal number. Ones complement of 0.1010. So now what is this? This is 10 power minus 1, 10 power minus 2, minus 3 and minus 4. Okay, so 1 minus 2 power minus 4 to the base 10 minus 0.011010. That is a given number. 1 minus 2 power minus 4, it is nothing but 0.9375 minus 0.1010. If I subtract these two numbers, first convert this 0.9375 into binary and then do the subtraction, and you will be ending up with 0.0101. Okay, this is ones complement. Easily we can even take the ones complement inverting all the digits after the decimal point, like this will be 0 1 0 1. That is what I am getting it here. Okay, so the problems, as I said, we need to process data in machines. So for processing those data in the machines, we are dealing with the r's complement and the r minus 1's complement. So let us implement these r's complement and r minus 1's complement by means of problems. Okay, so subtract 325 minus 125 using r's complement. So this is the decimal number. So r's complement is nothing but we need to use tens complement for the subtrahend. Okay, 325, I will take tens complement for the subtrahend and then I will add the result. Okay, then add the two numbers. Let me explain you detailedly. Minuend is 325. I'll keep it as such. Since this is minus 125, what I'll do is I'll take a tens complement for 125. Tens complement of for the number 125. How will I take? It is 3 digits I'm having. 10 power 3 minus 125. It is 875. So 325, instead of subtracting minus 125, I'll add 875. So 875 will add. The result is 200. I have a carry here. Here. If I have a carry, what I should do is, okay, if I have a carry, I will keep it as such. Okay, if I have a carry, I will keep it as such. Coming to your second problem, I will tell about carry shortly. Coming to your r's complement in case of your binary number. In case of your binary number, okay, if I have a carry, I'll ignore. Okay, if I have a carry, I will ignore. So there is a carry. I'll ignore the carry. I'll take up the result for the decimal number. Okay, I will take up the result for the decimal number. Next, I'll take with this. Okay, 10 10 100. Let me subtract it with 000 followed by 100. So 2's complement, r's complement. We are dealing with r's complement. So let me take 2's complement. 2's complement of this number and then I'll add. 2's complement of this number is nothing but first take 1's complement and then you can add 1. Okay, so invert all this. How I said about taking 1's complement, invert all the digits. So 1, make it 1 as 0 and 0 to 1, and then add 1 with the result. This will be the 2's complement of this number. Okay, so after that you add. Okay, if you after that you add after addition. Okay, if after addition you are getting this as a result. There is a carry. If there is a carry, leave the answer as such. This will be the answer. Okay, leave the answer as such. This will be the answer. Okay. For example, if you don't have a carry, okay, if you don't have a carry, for example, if this is 0, okay, if this is 0, so take 2's complement of 100 00 if no carry, okay, if no carry. Raise 2's complement of 100 00 and then insert a negative sign before the 2's complement of this number. That is the answer. Similarly, here also, if there is no carry, okay, take 10's complement of 200 and then insert negative sign before the 10's complement of 200. This holds good for the r's complement, okay, subtraction. Keep in mind this complement is used for the subtraction. Next thing is r minus 1's complement. R minus 1's complement, let me take the same number 325 minus 125. We know we should take r's complement of this 125. So how will I take? This is 3-digit number, so 10 power 3 minus 1 minus 125, this is 874. So add this 325 plus 874. So I will be having a carry. Okay, I will be having a carry. If there is a carry, okay, in 1's complement, this r minus 1's complement is just opposite to your r's complement, meaning after taking, if there is a carry, add carry with the this is end around carry, this is otherwise said to be end around carry, add carry with the result 199 plus 1, this is 200. After that, okay, what you need to do is if yeah okay, if you have an end around carry, if I have an end around carry, add the end around carry and keep it as a result. This will be the result. Actual result is this for your n minus 1's complement, meaning that 9's complement. This is the answer. If I have a carry, I need to add that to the result. That this will be the answer. This will be the answer for r minus 1's complement or 9's complement. Okay, and the next thing is let me take r minus 1's complement for a binary number. Okay, for a binary number. So again I have to concentrate only on the subtrahend. Choose complement of the given digit. After taking I'm sorry, I think this is 1's complement of the given digit. 1's complement is very easy. Just invert all the digits. So 100 100, take 1's complement. If 1's complement, after that add, okay, minuend plus the 1's complement of the subtrahend, add, I have a carry, okay, I have a carry. If there is a carry, again add and keep it as a result. This is the result. So in r minus 1's complement, if there is end around carry, we need to add it with the result. Okay, add it with the result. Okay, if there is no carry. So if there is no carry, what I have to do is, okay, if there is no carry, for this example 3250 minus 72532, okay, 72532, this is again r minus 1's complement for the decimal number, for decimal. Okay, so what I have to do, I need to take 9's complement of 72532, which is nothing but 1 2 4 5, so 10 power 5 minus 1 minus 72532 will be giving this answer 27467. Then this number I need to add with the 3250. So add this, I'll be having this as the result. There is no carry. If there is no carry, what I have to do is I need to take 9's complement of this number. If there is no carry, take 9's complement of the result and include a negative sign before. Include a negative sign before the answer. Okay. Similarly, you can even try for this binary, which is nothing but 100011010. Take the r minus 1's complement and check your answer. Okay, the next topic that we are going to deal is about binary codes. There are several binary codes. What is binary codes? The combinations of zeros and ones are said to be binary code, binary code. And since we are using zeros and ones, that is said to be binary code. Why we need binary code? We need to transfer, if we need to transfer some information from one place to another, we need this sorts of binary codes. Because machine language, as I said already, it can understand only zeros to ones. There are many classifications of binary codes, namely weighted code, non-weighted, error detecting code, error correcting code, telegraphic code, teletypewriter code, ASCII code, epicity code, and Hollerith code. Okay. And coming to the weighted codes, each bit position, and keep in mind all these codes will be having a combination of zeros and ones. So we have different types of weighted codes, 8421 code, 2421 code, and 5211 code. 8421 code is nothing but each digits will be given a weight. For example, the first binary digit is given 2 power 0, 2 power 1, because 2 power 0 is 0, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8. So it is called as 8421 code. Similarly, this is 2 power 0, 2 power 1, and 2 power 2, 2 power 1. So 2421 code. Okay, 2421 code. Whereas this 5211, it is a non-weighted code. Okay. These are said to be it is not a non-weighted code. Here also each position is given each bit position is given a weight. For example, the decimal number 0, it is equivalent to 0 0 0 0 0 0 0 0 0 0 0 0. So the first digit is given a weight of 1, the second digit is given a weight of 1, the third digit is given a weight of 2, the fourth digit is given a weight of 5. Similarly, here also the first digit is given a weight of 1, the second digit is given a weight of 2, the third digit is given a weight of 4, and the fourth digit is given a weight of 2. Is it okay? The second number is 1. Okay, the second number is 1. Look here, I'll tell only for these decimal number 1 and 2. So now for 8421 code, we need to represent this 1. This is 1. Where I will represent this 1? This only the first digit is 1. So I will make that as 1. Code is nothing but combination of zeros and ones. So this is 1. The rest all I am making it is 0. Again 2421. This is 1. The rest all I am making it is 0. And 5211. Again this is 1. The least significant bit is 1. So that is 1 and the rest all 0. Then 2. See, if I am making this as 1, then it will be 2 power 1, whose weight is 1. Am I right? I cannot make this as 1 because 2 power 1 is 2. So if both the weights are there, it is 2 plus 1. If I add, that becomes 3, the decimal number. So I cannot make this as 1. So I will be making this as 0 and I will be making this as 1. Again, in the same case for 2421 also, this is 0010. Whereas this one, okay, we have to start only from the LSB. Keep in mind. So we have 1 over here, 1 over here. Those two I will make it as 1 and 1. So if I add even the binary number, the decimal equivalent is 2. So 0011. Okay, likewise we need to frame all the decimal number into equivalent 8421, 2421 and 5211 code. This is said to be weighted codes. Each decimal or each position is given a weight. Okay. 8421 and 2421. 8421 is a sequential code. Okay. Sequential code means it will come in sequence, as like your normal decimal sequence. This is a sequential code. Whereas 2421 is a reflective code, meaning decimal number 9's complement of this is 0 0, because take the complement 1 1 1 1. If you take the complement, it's 0 0 0 0. If you look, 9's complement is 0. So 9 and 0 is a complement. Similarly, 8 and 1 will be the complement. This is said to be reflective code. This is said to be reflective code. And non-weighted code is nothing but each position is not given a weight. Hence, it is said to be non-weighted code. Example for that is a binary code and XS3 code and gray code. What is XS3 code is 8421 plus the, if I add 8421 code number plus the decimal number 3, meaning 8421 of 8421, okay. The decimal number 2 is nothing but in 8421 it is represented by 10. So 8421 decimal number 2 is represented by 0010. I need to add plus 3 decimal here, okay, plus 3 decimal here. 3 decimal is nothing but 0010 0011. If I add it, this is 1010. This is 0101. Look here, this is 01001. This is nothing but XS3 code. This is nothing but XS3 code. Whereas binary code will allow, gray code will allow only one bit change. 0011 0001. This is for 1. After that, only one bit change is allowed. So what I'm doing is at least one of the digits should be 1. One of the binary coded digit should be 1. In that case, if I if I use 0010, I'm changing LSB as well as the second LSB. That is not allowed. Only one bit change is allowed. Okay. So what I'm going to do, I'm making this as 1. I'm keeping it as such. So it will be 0011. Only one bit change is allowed for your gray code. And the error detecting code, I'll just brief you, go through by yourself these as an assignment. Error detecting and the correcting codes, it is used for error detecting code. Usually the 8th bit is said to be the parity bit. The parity bit is nothing but if you have even number of ones in the result and odd number of ones in the result, accordingly it will be called even parity and the odd parity based on the result. If for example in the sending end, if I'm sending an even parity digit with even parity, meaning it has even number of ones. In the receiving end, if I'm receiving it as odd parity, meaning odd number of ones, then whatever data that I have received is wrong. That is to be error detecting code. Error detecting code, after checking this parity bit, how to correct that data, that can be done by using Hamming code or another continuous codes. Okay. And other than this, you will be having ASCII and the ABCD code. ASCII code is used in the laptops for all your characters, symbols, etc., using your computers, and it is said to be American Standard Code for Information Interchange. Whereas extended binary code, which is nothing but EPCT, extended binary coded decimal interchange code. This is used for IBM computers. It is an 8-bit code. Okay. So telegraphic and teletypewriter codes are left as an exercise for the readers. Okay. So we have discussed R's complement, R minus 1's complement for both decimal and binary, and I have given a brief introduction about the codes, binary codes, namely weighted and the non-weighted codes, and I said about what is error detecting and the correcting code. This, and I have left exercise for you about for the telegraphic and the typewriter code. Thank you.